Hi, so today I'm going to introduce ThreeJs. Um, Let me get the slide up. So I'll be following from a book called Learning ThreeJs by Dirksen. This is available from PacT Publishing, but I'm going to follow along pretty closely to what they do, so you probably won't need the book. One thing we can get from the book is the source code. This includes the whole of ThreeJs, as well as any libraries you need. It's available from GitHub at this location. Another really good resource is the threejs.org website. This has a huge manual for ThreeJs, along with lots and lots of examples for doing various things with ThreeJs. Recently, I found a fairly detailed introduction in free chapters of this unfinished book, Discover ThreeJs. To start off with, all of ThreeJs works from a basic skeleton code that we have to provide for it in HTML. Required is the JavaScript, the ThreeJs libraries, jQuery, a style sheet, and then down here a function where we put all of the ThreeJs stuff. This differs a little bit from the way we did it, where we wrote our JavaScript in a file and included it. You can do it that way as well, but I'm going to follow along the way the book does it. So in that function that's run when the window is loaded, the function here that's run when the window is all loaded, we're going to do a number of things. We're going to initialize a scene, make a camera and a renderer, and set the clear color and window size. These are all done by constructing a new ThreeJs.scene, a new perspective camera that has a field of view and a window width and, well, an aspect ratio and a near and far. These are familiar from what we've done with other cameras. We're going to do a WebGL camera. We set the clear color here with a hexadecimal number, and the window size is the window's inner width and inner height. This is the whole screen window. In this first version, we'll create a couple of objects. We'll create a plane for the ground. And to do this, we make a 3-dot plane geometry that's 60 by 20. I believe the units are considered to be meters. We create a material. This is a mesh basic material. We'll see that there are a number of different kinds of materials that we can do. And again, this one has a color. Again, we're establishing with a hexadecimal number. These are sets of bytes. So the red is the CC, green is CC, and blue is CC. So we're going to end up with a gray color. We then need to make the plane, which is a mesh. So we're creating a mesh with a plane geometry and a plane material. This is the plane geometry, and this is the plane material that we just made. We then need to rotate and position the plane. So we give the plane's rotation in around the x-axis minus half a pi, and we put its position at x equals 15, y equals 0, and z equals 0. And then we add the scene to the plane, add the plane to the scene. another object, a cube. In this case, we're establishing a cube geometry, again, a mesh basic material, this time with a red channel that's FF and the other green and blue 0. And then make the mesh, position it at X, Y, Z, and add it to the scene. And finally, a sphere, which we'll do this time as a wireframe, a sphere geometry. I believe this is the radius, and then how many subdivisions in latitude and longitude that we want. A sphere material, now a kind of bluish color, mostly in the blue, with the wireframe set to true. Again, making the mesh, positioning it, and adding it to the scene. We need a camera. We made the camera back at the beginning there. It was a perspective camera, but we need to position it. So we just put the camera at X, Y, and Z, and then we make the camera look at the scene position, which I believe is 0, 0, 0 in the coordinate system. We need to attach this to the HTML render element. So a WebGL output is appended to the element in HTML. And we can then trigger the renderer to render the scene with the camera. And that's all there is to that. And this is what this looks like. We've got our gray plane, we've got our red cube, and we have our wireframe sphere. So that's all pretty simple, straightforward. So there are a lot of different geometries that are available. In 2D, there's a plane, a circle. In 3D, you have cubes, spheres, cylinders, toruses, tori, torus knots, polyhedra, icehedron, octahedron, tetrahedron, and various shapes that we can define with a curve. We can do things with these shapes like turn them on a lathe or extrude them or build them parametrically. And they're text objects too. Here's a sample scene that shows the various different objects that we can build just by asking for a particular shape in the same way that we ask for a sphere, a cube, and a plane. So that mesh basic material that we used was the simplest one, and it's a material that doesn't interact with lights. And we're going to add lights soon. But in order to do that, we have to have a material that interacts with lights. And the simplest of those is the Lambert material. Remember Lambert's law that the strength of the light depends on its angle from the horizon. And the Lambert material has two options, a color and an emission. So we're going to add a spotlight to the scene. Spotlights can cast shadows. So here we specify the new spotlight with a color. FFFFF is going to be all white. We can set the spotlight's position, and we can have the spotlight cast a shadow, and we can add it to our scene. If we want to have shadows on the renderer, we have to turn on the shadow map. So shadow map enabled is true. If we want objects to receive shadows, we have to explicitly say that they both receive and cast shadows. So since the plane has nothing below it, we'll just have it receive a shadow, and we'll have the two objects above the plane cast shadows. And so I believe both receive and cast shadow is false by default. So here's our scene. And again, second scene, we now have clear shadows of our objects. The light's over here, casting light in this direction, and casting shadows. We now have a Lambert material, which now shows shading. Notice it doesn't have any shining spots. That's not something that we're going to get until we go to another kind of material. So that just drew a single scene. When we did the renderer.render scene in camera, that drew one picture. So what we need to do now is add the loop that's going to continually redraw our scene so that we can have an animation. And we're going to use that same request animation frame that we're familiar with from our author's code to use that to generate a loop. So instead of renderer.render, I'm going to replace that with a step counter that I'm going to use to control things. And I'll call a render function, where the render function is going to rotate the cube and bounce the ball and render the scene. I'll explain stats update in a second. But here we're going to rotate our cube about the X, Y, and Z axes, so it's going to kind of spin. We'll use this step that I initialized before with some math cosine and sine functions to move the sphere back and forth in X and Y. Then I'm going to request an animation frame that calls the render function itself again. And then I'm going to do a renderer.render scene camera. So that's going to draw the picture, and we'll see something that looks like this. We have our bouncing ball, and we have our rotating cube, and notice the shadows update, and everything is all quite copacetic. So that stats update, this puts a little frame per second meter in the upper left corner. We do have to add something to the HTML for the stats. We have to add a library, stats.js, and we have to put a stats output in the HTML. We also need a function in our JavaScript init stats that makes a new stats, sets its mode to be either 0 for frames per second or 1 for milliseconds per frame. And then we need to position it somewhere in the frame. In this case, absolute coordinates 0 pixels from the top left corner. And we need to append that to the stats output here and return the stats. So that's this little picture that we see up here in the corner that is showing us the frame rate, and it's pinned up somewhere at 60, which I believe is what the browser limits our frame rate to, 60 frames per second. So the next material is the Fawn material. And as you might suspect, the Fawn material is used for shiny objects with specular highlights, shiny spots. This is basically based on the Blinn Fawn lighting model. It has color and emissive, but it also has ambient and specular. And so in the Fawn material, we're going to see this looks like this. Now, I have a material. I'm going to explain in a little bit how these menus work. But this menu is a system that we'll look at. So here the ambient light color is turned way up here. So if I turn the ambient light down, we can see saturated ambient light makes the object look yellow. And I'll turn the ambient light off. We can't really see specular highlights too well on the cube, so I'll put in a sphere. Here's our shininess exponent. the specular color has to be turned up too. So here I'll make a red specular spot, and the shininess makes either a big diffuse specular highlight or a very shiny tight one. This is the basic color of our object, and we all have the option of an emissive color, which of course overwhelms any color that we've got here because now it's emitting color. We also have a transparent option where I can turn down the opacity of my object and see it kind of disappear. So the menu interface is just available here from a GitHub. There's a tutorial, several page tutorial that shows you how to set up various aspects of these menu systems. They have a lot of options, including these color pickers and booleans and sliders and choice pull downs. It's all described in fair detail at that website. But basically what we need to do is add to our HTML the dat.gui library. And then in our JavaScript, we have to add controls. Where we have controls as a new function here that has the initial values of all of the different options, the rotation speed, the bouncing speed, the opacity, and so forth. These will be the initial values that show on our menu. We need to add a new dat.gui object, and with that object, we have to provide callback functions for all of the items that can change. So all of these items that are going to show in the menu, we have to be able to change them. We have to have callbacks that handle that. So the SP GUI here is a folder within the main menu. So here we have a mesh outer folder, and then we have opacity, transparent, visible, and so forth. A lot of these have on change functions. So if the opacity, which has the default 0 to 1, changes, what it's changed to is returned in the argument E. And so I can set my mesh material opacity to that argument. Transparency, the Boolean, here's a color changer. So an add color gives me one of these color changers that we see over here. We have one for ambient, emissive, and specular. And on change, we assign the ambient, emissive, or specular to that new 3 dot color of the appropriate argument. Some of them can be a little more complicated. This picker here for the side, whether we're going to show the front or back face. So we have controls that have the different choices. This is the side that's shown here, and then the 3 different choices, front, back, and double, that are shown here. And on change, I can print it out to the console, but I'm using a switch here, case front. I'm going to set the material side to front side, and back side, and double side. And I need to update my material when I make some change to it. Otherwise, it doesn't show. The add color. And here the select mesh, selected mesh, cube, sphere, or plane. On change, I'm going to remove the plane, cube, and sphere from the scene. If it's not there, it doesn't matter. And then I'm going to add back the one that I chose with the menu. You guys all have labored over making the trackball interface, but in Three.js, it's trivial. We merely need to add the trackball controls library. We need a clock, so we make a Three.js clock. After the camera lookout, we can add our trackball controls. The trackball needs to know what camera we're looking through, and there are various settings for how fast it rotates, how fast it zooms, how fast it pans. And then in the update, in the render function, we need to add an update to the trackball controls that takes this delta that it gets from the clock. This is basically the frame rate, I believe, the time interval of the last frame. So with that, we have now a trackball interface. Put a cube and make it opaque. And I'm getting an internet connection is unstable. I'm gonna close this, and I have to go to my library here. No, that's not useful. Well, it's a trackball interface with a little town scene. It's fairly easy. I think the scroll button, the scroll zooms, right mouse pans back and forth, and left mouse rotates. Notice the frame rate over here. So there's also an orbit camera, a fly camera, and a first-person interface. I'm not going to go through them. I'll let you look at them yourself when you have a look at the examples here. We did an RGB Color Cube where we had separate colors specified at each vertex. And it turns out to actually be non-trivial to implement this in Three.js. We were using a basic material, one that didn't interact with the light, where we were defining a color at each of the different vertices that went with the faces. So to make an RGB cube of a particular size, I'm going to get a material that's a mesh basic material. And in this case, I have to specify the vertex colors are of type, are 3 vertex colors. Let me get that one up. So this was our familiar cube that we played with before, that you guys were generating. So we define the cube geometry, setting cube geometry to have its size. And now we need to assign colors to the vertices. I extract from the cube geometry vertices array that's length long in this loop. I'm going to pull out the ith vertex into point. I'm going to assign a color to that, and I'm then going to override that color by using a set RGB whose value is an RGB based on the point size, the point X, Y, and Z coordinates divided by the sign of the ball. And I'm going to use this array. I'm going to put this in the cube geometry array colors. What makes it a little complicated is that the colors have to be assigned on the face indices rather than on the mesh's vertices. And the face indices are indexes A, B, C, and D, the quadrilaterals of the sides of the cube. So with face indices A, C, and D, looping over the geometry faces, these are the sides of our cube. There should be 4 of these, and getting each of these faces where the number of sides is a face is an instance of 3 faces. It's either going to have 3 or 4 edges. So if it's a triangle, it's a 3. If it's a quadrilateral, it's 4. Then we loop over the number of sides and assign each of the face vertex colors J that are pulled out of the face indices J. The colors, the face indices are A, B, C, and D on the vertex index on that face. And then we assign to each of those the appropriate colors, create our mesh of the cube geometry with now this vertex color material, and we can return that. Finally, we had a spotlight in one of those scenes, but there are also ambient lights, point lights, directional area lights, and a hemisphere light, which we haven't seen before. None of, and there are examples for all of these that I've included here in the example: ambient, directional, point and spot, and hemisphere. The only one you might not be familiar with is the hemisphere light, which is one that has a ground color and a sky color, and it kind of casts the ambient light gets color from above and color from below, and I can turn the intensity up here. And whoops. Well, let's make this red. So now the ball here has kind of a reddish tinge on the top and blue from below. That one's not showing up very well. Oh, here, because I haven't got the hemisphere light turned on. There it is. So red from below, blue from above, as the ambient light of the scene. The ambient light. So that's a hemisphere light. And of course, the other lights are familiar. Area lights are pretty cool. They interact with objects around them. We can change their color, do all kinds of stuff. Point lights, a point light. Point light. I believe this is the example I showed in class with a point light. It has a range, it attenuates with distance, and we can set all of those. And the spotlight, of course, makes a cone of light. We haven't, you notice I haven't mentioned shaders in here at all. We don't use shaders. Well, we can use shaders. We can write them ourselves. So there's an example here with custom where we have all kinds of weird stuff going on the different face of our cube with all kinds of strange things happening here, cloud shaders and Perlin noise, kind of a reflection here. And these individual shaders, I'm making a mesh material that uses fragment shader 1, fragment shader 2. Each of these materials uses a different fragment shader that we must provide. And then here on this mesh face material, I'm putting different materials on each of the faces of my material. Well, I'm putting all these different materials on different faces, and then I have a cube that uses that material. And as we write our own shaders, we have to specify attributes and uniforms. The projection matrix and the model view matrix are taken care of automatically. We don't have to do that. So when I want to create a material, like I did back here, material, a vertex shader and a fragment shader. The vertex shader I think is all the same, but it's using different fragment shaders. So the vertex shader we get from our document, and the fragment shader we also get from our document by ID. So our shaders would have to have these appropriate IDs to match up in the HTML. And here we specify the attributes and the uniforms. There are no attributes that we're specifying, but we're going to have time, scale, alpha, and resolution. And the values that we're setting for these, the uniform resolutions, X value is the window width, and its Y value is the window height. And then forming that mesh material with the shader material, we have to specify the uniforms, the attributes, the vertex and fragment shader that we're going to use, and return that mesh material. With something like this that varies with time, where something is going on in it, we're going to be passing the time into the shader. And so in the render function, we have to specify for each of the specific materials here, the uniform time value that is updated for each of those. And I believe that kind of finishes this initial foray into ThreeJs. And so I'm going to stop the share here. I'm going to stop the recording, and we'll see how this works. I'm going to stop the recording, so have fun watching this. I went very fast to make it as short as possible, and I'll see you in class. Bye.